So the previous class we referred to the requirements analysis part, and once the requirements analysis part is that you're clear as to what are the requirements the customer has got in terms of performance, and that could be with with respect to takeoff distance, landing distance, sustained turn rate, range, number of passengers, endurance, depending on the type of aircraft which is being designed. The requirements will be there. So after that you have understood that requirement, the first step in design is to try and estimate the overall takeoff weight. Okay, so that is the first estimation. And then after that takeoff weight is estimated, the next step is to derive what's called the constraint diagram. So constraint diagram is a way to reduce the design space or limit the design space involving wing loading and takeoff thrust loading, so that whenever you choose a thrust weight ratio or wing loading, you're ensured that the performance requirements, whatever is there in that, is met. So that's the idea of constraint diagram. We will go through both these aspects now. So essentially, at the end of the sessions, you will understand, how the basic design starts. The first part is, collating important statistical data from various existing aircrafts, and from that you can derive correlations and thumb rules. Correlations, for example, number of total passengers in a jet aircraft to the total weight of the aircraft, or for the range of the aircraft to the total weight of the fuel, the empty weight of the aircraft to correlation to the total number of passengers payload, and stuff like that. And you have such correlations published in open domain, available as curves, graphs, and also as some cases equations for the curve fit. So these are used as a way to get an idea whether what you're doing is within the ballpark or not. So these are not to be used fully, but to be used to check the numbers you get from different techniques. Are they all similar and all they fall in the same bracket, so that you know that you are realistic. Okay, and then you also have to perform preliminary weight estimation. This depends on looking at the payload the aircraft is supposed to carry, and looking at the fuel it is supposed to carry, and any other devices. So in long range passenger aircraft, fuel component is quite significant. In the combat aircraft, the fuel component may not be that significant, but the payloads in terms like bombs or missiles or drop tanks or anything else, they become important. So we will have two different techniques. Once we will use the statistical data, and we'll also have detailed weight estimation depending on the kind of fuel consumption and type like that. And then from there, we can cross-check the assumptions we have made in computing either one of the ways to result. So essentially, it's some kind of a sensitivity test for the end results. Then, of course, use of requirements to drive constraints on the thrust to weight ratio and wing loading. So because these two are very important inputs of an aircraft, wing loading and thrust to weight ratio. Based on this, entire performance, or at least most of the performance parameters of the aircraft can be derived. So if you are told now that this landing distance should be less than certain length of the thing, that will tell you what should be the stall speed and what should be because the approach speed and stuff like that. And also, if you are told this is the kind of rate of climb you expect from this aircraft, that will tell you what should be the thrust kind of availability. So just as a matter of interest here, thrust to weight ratios of most combat aircrafts are close to 1. Some of them are more than 1, some of them a little bit less than 1. And all the passenger aircrafts, long range passenger aircraft, the thrust to weight ratio is somewhere between 29 to 33%. Because in a commercial transport aircraft, the fuel consumption and hence the cost of running the aircraft, in terms of number of kilometers, cost dollars per passenger kilometer. So that's very, very important. They would rather have as low thrust as possible, because passenger aircrafts are not expected to do very steep turns or dive pullouts and stuff. However, in a combat aircraft, fuel consumption rate or the economy of fuel consumption is not the primary criteria. If it is good, it is acceptable, but what is important is the functionality. If the aircraft has to do 18 degrees per second turn rate, sustained turn rate, it has to do that. Doesn't matter. For that, if you need a very low wing loading and a very high thrust loading, so be it. Okay, so that depends on the kind of aircraft you are designing. So the design process itself starts with the estimation of three key parameters. One is the gross takeoff weight, followed by wing area, SW, so S suffix W, and the thrust or the power required. Okay, once you have these three, everything else will follow one by one through systematic design process. So from these three things, you derive what is called wing loading, W by S. That's in number of newtons every square meter of the wing is carrying. And then you also have the thrust to weight ratio, or for every power to weight ratio, for every Newton of weight of the aircraft, what is the Newton thrust or what is the kilowatt power you have. And these two things, wing loading and thrust to weight ratio, cover most of the performance parameters, as also the aircraft cost and complexity to a great extent. So if you have seen most of the passenger aircrafts, their engines are massive and they are extremely high bypass, essentially sometimes even 10 or 11 bypass ratios, and they are very, very fuel efficient, almost as good in terms of fuel consumption as the old propeller and piston engine aircraft. Whereas in combat aircraft, we cannot afford to put such big diameter engines because the diameter increases because of the bypass ratio. So if you cannot have 9 to 10 bypass ratios in a combat airplane because there the engines are actually housed inside the fuselage. So all said and done, some of the modern combat airplanes do have a bypass engine, but the bypass ratio is 0.5 or 0.6 or something like that. So the complexity of the construction, complexity of the maintenance, and of course the cost of the aircraft are all dependent on the kind of wing loading and thrust to weight ratios you have arrived at. There are two methods followed across the world, and one is based on the past data of similar aircraft correlations. When I say weight estimation, it's only estimation, right? It's the first iteration, way to start your design process. It's not going to be the final one because final one depends on what material you've used and everything else. But you got to start somewhere to estimate the wing loading. To estimate the wing loading, you need to have the weight estimation. So there are two basic techniques, as I said. One is based on existing similar aircraft. Suppose you are asked to design a 100 passenger aircraft with a 6,000 kilometer range. Then it is very close to some of these new Boeings and Airbuses. So if you look at their data and see, what is their fraction of total weight to the fuel weight, what's the fraction of passenger weight to the total weight and stuff like that, your design it's not going to be very different from the existing Airbus or Boeing. If anything, your design may be slightly more efficient because of the development in terms of materials and newer techniques and stuff. Okay, so that is where you start with an estimation based on existing aircraft data. So, however, you have to ensure that you're taking the same data of similar aircraft. If you're designing, let's say, a combat airplane similar to Rafale or Tejas or F-16, there's no point in you collecting data with respect to Airbus and Boeings. Okay, and similarly, if you're looking at designing a passenger aircraft, there's no point in looking at data from F-16, F-14 and stuff like that. So you have to look at appropriately, select aircraft which are appropriate to the design you are developing. Sometimes in the development of new materials means lighter structure. So you could expect your design to be optimistically a little lighter in the sense that the empty weight to the total weight fraction to be slightly less than existing. There are also continuous improvements in the specific fuel consumption of the engine. So there too, you will probably for the same range be using less amount of fuel and maybe the engine also is a little lighter. This is one technique, one approach process, and we'll of course also use the other approach process, and that is driven by performance requirement. Any aircraft comes with either a requirement of range and endurance, and from this you can estimate the kind of fuel consumption you're having, takeoff and landing, and this will dictate the kind of wing loading and L by D ratios you are going to need. Acceleration and rate of climb, and these will be dictated by the thrust to weight ratio. So you can use both the techniques to arrive at the weight, total weight estimation, and then see if they make sense. Because if you get wildly different numbers, then there's something wrong. That's not going to happen. You will get numbers which are very close to each other. So that will ensure kind of a sanity check on your process, both the statistical data correction and also the method of using performance to estimate the weight. Okay, so let's look at a very simple and almost crude method of estimating the weight. This has been used in many places as a starting point. Okay, so let's look at the takeoff weight, total takeoff weight. We can bring it into first, drop it into four compartments. The first is the payload weight. This is the weight of this stuff you have to carry. Now, this stuff you have to carry, maybe the number of passengers, maybe the number of missiles and bombs, or maybe the cargo, if it's a cargo plane. So this is the one for which the entire aircraft is designed and made to fly. This is the one which pays you money. So that's why it's called payload. Okay, and the crew weight is the crew which is needed to fly this aircraft. Now that depends on the nature of the thing. If it's a commercial passenger, you would have seen that there is a pilot, co-pilot, and a bunch of stewards, air hostesses, and stuff like that. So there also there is a regulation which says for the n number of passengers, you should have one flight attendant. Now, of course, it doesn't say what kind of flight attendant, but one flight attendant is required for let's say n number of passengers. So if you have 5n passengers, you would have 5 flight attendants other than the pilot, co-pilot, and the any other person which is there inside the cabin. So this is the crew. Okay, so then the next one is the fuel weight. It has to carry some fuel, and that fuel is needed for the journey it's going to make, the distance it's going to travel, how long it's going to travel, and some reserve ratios and stuff like that. And the last one is empty weight, meaning all the rest. So your entire aircraft weight is broken up into payload weight, crew weight, fuel weight, and all the rest as WE. So if you write it as an equation, WTO is WPL plus WC plus WF. Okay, here you see the payload weight and the crew weight, they don't depend on anything, because that is what is the requirement. You need to carry 100 passengers, you need to carry 100 passengers. 100 passengers come with 5 flight attendants. Yes, that is flight attendants. Now, they don't depend on the takeoff weight. They are independent. Okay, and they can be calculated independently. So how do we calculate independently? For example, if you're looking at a combat airplane and it is supposed to carry 4 missiles and 3 bombs and a certain amount of bullets, because most of the combat airplanes do have an onboard gun, and you can estimate the weight of the bullets for that, and you have weight of the gun, and you can also estimate each missile has its own weight, so you can estimate the weight of those payloads. Or if you are told you have to have a passenger aircraft with 100 people, 100 passenger payload, then it is a little bit of approximation. So you assume that every passenger is 80 kgs mass, and every passenger is allowed some 20 kgs of baggage. So 80 plus 20 is about 100 kgs is the mass. You can add another 10 kgs for the amount of consumables he will be probably using, like food, water, and the chair and all that. So 110 per passenger. So 100 passengers will be 110 into 100. Okay, we will get the actual numbers. I'm just giving you so that you understand where we are going. So, and 100 passengers, if you say the regulation says 5 crew members, and for those crew members too, you have the same weight, 110. So 100 passengers plus 5 crew members will be 105 into 110. That will be the weight of the passengers and crew. Now this it does not depend on the total weight. Now they may go entirely in a jam-packed in a aircraft, or they may be only 100 passengers with fly crew in an Airbus 380, which is a huge aircraft. That doesn't matter. So that what the point I'm making is they can be calculated independently. Okay, whereas the weight of fuel F and the empty weight. So I'm sorry, there is a term missing here. That's a WE term. So I'll add that. So that and the fuel weight, of course, depend on the kind of aircraft and the performance which are needed. So where the empty weight is the weight of the all the rest of the things, like the engine structures, the landing gears, and lubricating oil, and everything else other than payload, crew, and fuel. And these two, the WE depends on the nature of the aircraft, also the overall weight of the aircraft. They are part of the fraction. Similarly, fuel is a fraction of the aircraft's weight, and you can use past data for their percentages, as well as you can do a detailed estimation based on the kind of fuel consumption and stuff like that. If we rewrite this equation, okay, and we can rewrite this equation as W takeoff is equal to weight, payload weight, crew weight, and then fuel weight divided and multiplied by total weight. I just done this so that there's no change in WF remains same, but I need to get this fraction. That is why I have written this way W fuel weight multiply and divide by takeoff weight. Similarly, empty weight multiply and divide by takeoff weight. So if we take these two terms to the left hand side, all the terms involving W T naught takeoff weight. So you have takeoff weight minus fuel weight fraction into takeoff weight minus empty weight fraction into takeoff weight is equal to payload weight and crew weight on the right hand side. So this we can simplify into saying that W takeoff weight into 1 minus fuel fraction, empty weight fraction is equal to payload weight plus crew weight. Right. So rearranging, we can get in terms of takeoff weight is equal to payload weight, crew weight divided by 1 minus fuel fraction and empty fraction. Now, the numerator we have already estimated, depending on what the aircraft, you estimated WPL and WC. But where do we get this fuel fraction and empty fraction weight? This is where we look at the existing aircraft and statistical data. And also, based on the nature of the aircraft, you can initially make a guess as to what kind of engine it's likely to use. Okay, let me explain that. Suppose you're designing a two-seater passenger aircraft, a two-seater trainer like the ones you see in our ground. Okay, what engine it's going to have? It's not likely to have a turbojet engine. It's unlikely to have a turbofan engine also. It's most likely going to have a propeller-based piston engine. It's a trainer, small little trainer. So propeller-based piston engine aircraft, they have a fuel consumption of some things in terms of newtons per newton, newtons per kilowatt per second. So that will give you an estimation of the kind of fuel consumption is likely to have, SFC. Now, if it's an aircraft is going to fly 6,000 kilometers, then obviously it's not going to be a propeller-based aircraft. It's going to be a turbofan-based aircraft. And turbofans come with a certain amount of fuel consumption. And based on that, you can estimate the kind of amount of fuel, number of gallons of fuel you're likely to use in that flight. So all this can be used either from statistics, and generally statistics is also checked, as well as detailed estimation for you to arrive at the first approximate estimation of the takeoff weight. Okay, now let's start looking at some existing correlations. So typical crew weight ratios. If you take a hang glider or a kite paraglider, crew weight ratio WC by WT nowadays 70 to 80%. This is obvious because there is only a human being with a glider attached to him. Okay, but if you look at these aircraft, bombers, okay, or large jet trainer, then you will see a jet trainer has 4 to 8% is the crew weight, because that trainer will have two people, the trainee and the trainer, and it'll be a small aircraft anyway. Okay, similarly, large transport aircraft, the crew weight will be very, very low, 4 to not even 4.4 to 8%. The reason is most of the large transport aircraft will have two pilots, maybe one navigator, and some flight attendants. So the maximum weight you would see in smaller ultralight and microlight and these kind of things. So crew weight will be very, very small if you are somewhere in this domain. For example, Genser Aircraft Company, the small aircraft company in Bangalore, they are designing a business jet. It will take about 4 people with the 1 pilot and 1 attendant maybe. And that is the crew weight will be about 1.5 to 3%. Bombers will have less because their bombers don't need flight attendants and they have only pilot, co-pilot, and sometimes a flight engineer who is a navigator as well. And that's it, nobody else. So that's a very, very low percentage of crew weight. Now let's look at the empty weight ratios. I'm sorry, it's not very visible since anyway you're going to get all the slides after I finish through them. You can look at them in detail later, but I'll just go run through some things. So these are empty weight ratios of a host of aircraft, data collected over a period of time by different people. And in this, some of the aircrafts you would recognize. ATR 42 is a regional transport aircraft. Now the ones flies between Bangalore and Chennai. So there, if you see the the empty weight ratio is about 60%, 61%. Okay. Now, similarly, if you look at F-16 Falcon, is 67%. And if you look at Boeing 777-300, it's about 52%. Okay. And one important thing, if you see in the last column, almost everything except maybe one odd couple of things here and there, or almost all of them is 50% and above, slightly above. Okay, a few things like Walmart's is a hang glider, that is 35%, and similarly sailplane is 33%, but rest are all much above 50%. Or the best you have is about 50%. So you can straight away say WE by WT naught is 0.5 as a starting guess from this data. Or if you have better information, you can look at this. Airbus 380, 341 is about 48%, Boeing 777 is 52%. Okay, so in this equation, W by E by WT naught, you have a good guess about what they are. So that's going to be 0.5 kind of thing based on existing aircraft kind of data. And there are also different correlations. So that is one thing. And there's another correlation which relates to WE empty weight ratio as a function of takeoff weight plus a constant. This is just a linear fit, and there are numbers given here for jet transport, trainer, fighter, business, and all that. So these are derived by people, not by me. It's available all in textbooks and stuff like that. And they have been tested over a period of time. So the best thing would be to use all possible methods of estimating the weight and then correlate them all together and see which one looks most reasonable, or blindly take an average of all the possible estimates. Because anyway, the WTO is going to change as and when we go into detailed design, we start looking at the materials needed for wing, materials needed for fuselage and stuff. So the weight keeps increasing and then you get better and better approximation of the weight. Now here is an empty weight to takeoff weight correlation for fighter aircraft. So this was for all kinds of aircraft, including business and all that. So in the Nicolai's book on design, what you have is a correlation for fighter aircraft. And if you see here in the right hand side, that includes almost all the fighters in the Western domain, right? F Phantoms and F-16s, F-117s, F-15s, and F-15E, almost everything like that. So here on the x-axis, this is in pounds, but since we are looking at ratios, it doesn't matter what the unit here is, because we are, as I said, no, it's a ratio. Takeoff gross weight, let's say it's 100,000 here. For 100,000, if you are looking at ranges between 4,000, no, sorry, not 4,000, 40,000 to 50,000. So that's the roughly the same kind of thing. In this case, you have three curves here. One is you can see air to ground, and so the way empty weight correlation is given. Then there is different kinds of aircrafts like developmental aircraft, and then there is heavier aircrafts. All of them, if you can expect them to have a load factor of above 7.33. And these are conventional metal structures. So if you're designing a fighter plane and expect it to have a load factor of 8, and you're using conventional metal structures, and you expect the total weight to be 100,000 here, 1 lakh, then you can expect the empty weight to be around 65,000. Whatever mass, 65,000 mass, 65,000 newtons, depending on which unit, but the percentage is around 0.6. This is from a host of fighter planes, and as you can see, most of them fall on a similar correlation. So they're not likely wrong. Only difference is these are conventional metal structures. Maybe now you're looking at replacing some part of the metal structure by a composite structure. Maybe the wing is partly composite, the horizontal tail is partly composite. So then you can expect to have a slightly lower empty weight ratio than this. Otherwise, you will fall more or less on the same ballpark as this. That is for fighter planes. Now, if you look at bombers, they are very well correlated because all the bombers are, the ones from Boeing and everybody else, all of them form bang on the line. You cannot get a better correlation than this in terms of, total gross weight, total gross weight up to the total empty weight correlation. But even here, you see, if you take this point, 100,000, you are looking at 60,000. So all of them, you will see that the best you can get is about 50% empty weight. To reduce below that, it will be very expensive and also difficult to fabricate and maintain and all that kind of thing. So this is from the Nikolai's book on bombers. And the same Nikolai's book also gives you a civil aircraft, empty versus takeoff. And this too is an extremely good correlation. All the data points fall more or less bang on the line, and you can have a correlation here. So even but anyway, all the figures I showed, if you look at 100,000, most of the things end up around 60%. So as I said, empty weight fraction, 60% is more or less the first assumption everybody makes. And the next fraction you want to estimate is the fuel consumption. Okay, and then if you want to look at the breakup of weight, in case you're interested, how much is the wing weight and how much is the fuselage weight? Why we need this is, as I said a little time back, if I'm looking at changing the wing from metal to, let's say, carbon fiber composite, then I can look for a little weight reduction here or a certain amount of benefit of the weight. So if you look at wing weight of Airbus 300 is 44,000. I think they have given in pounds only. Most of the American books are in pounds, but for us it doesn't matter because we are looking at ratios. Airbus 300 is 44,000 pounds and 747, the jumbo jet, is 86,000 pounds. So wing itself is a significant weight. Okay, and of the total structure, if you see this line here is the total structure weight. Out of the total structure weight of 106,000 pounds, 44,000 is the wing. Okay, so now if you are looking at, let's say, changing the nacelle or the empennage or the wing with a different structure, you can get a better estimation here, and then also look at altering your empty weight fraction, which you used in the takeoff weight estimation. So that's the reason these kind of things are given so that you will be able to. But some things you can have a definite weight. For example, if you choose an engine, let's say you're choosing a Pratt & Whitney engine, with that some model will give you exactly what's the weight. So that will improve your weight estimation by putting in more realistic numbers for the engine weight itself, along with the fuel weight. So similarly, typical fuel weight ratios. Fuel weight anyway we'll estimate in detail, but this will give you an a kind of flavor what it's likely to be. And if you see this point here from Airbus 380 and Boeing 777, they are around 41-42%. And Global Hawk, this is unmanned reconnaissance craft, which is supposed to have a huge range, 24,000 kilometers range. There, the fuel weight is 63%. Okay, and Voyager is a circumnavigation, something which is going around the Earth. There too, the fuel is 72%. Whereas in a fighter plane like F-16C, you expect the fuel fraction to be somewhere between 12 to 15, 12 to 16%. So that's what you can see here. Okay, so this gives you fuel weight ratios also as a way to start your approximation. Now, one way to estimate the fuel weight in a little more detail than just looking at existing aircraft is to look at its mission profile. Okay, so this is a simple mission profile where the aircraft takes off. It starts from point 0 here, rolls, and at the point 1 it has taken off, and then it climbs to its cruise altitude, which is 2. Okay, from there it cruises up to 0.3, the 0.23 and all are not geographical thing, just to for this figure. Point number 3, it cruises up to that. Then it has reached its destination, so it descends. Once it descends to a landing zone, it's possible that the runway is busy. Then the aircraft is supposed to loiter, meaning circle around for a while. So from 4 to 5 is the loiter part, and then 5 to 6 it's final descent, and 6 to 7 it's landing. Okay, now if you look at the fuel fractions, what is the total consumption of fuel? That will be fuel weight, which what you have got at the 7 after all the consumption, divided by initial weight, that is W7 by W0. Okay, now this is a very simplified profile of the flight. Now, depending on different aircraft, you can come out with the difference. So combat airplanes can have a longer loiter zone, or shorter cruise zone, or some passenger aircraft can have a longer cruise zone and stuff like that. So essentially, something like this you have to draw and then arrive at this. W7 by W0 is what you are interested in. That is end weight of the aircraft, end after fuel consumption from starting weight. Now, if you look at 0 and 1, so from W1 to W0, I can write. I don't know the values, but as you will see, everything will eliminate itself out. So W1 by W0, similarly W2 by W1, and W3 by W2, and W4 by W3. So always the end point by the starting point if you take these ratios. So what actually happens if you multiply all this, you will end up with simply W7 by W0, because W1 cancels, W2 cancels. What you'll be left is W7 and W0, which is what you want. So the question is, what's the big idea of putting it this way? You can estimate individual fractions with little more accuracy than starting from 0 to 7 straight away as estimation. Okay, now over a long period of time, people have collected data. How much fuel is spent normally in an aircraft, where it is from starting point to its takeoff velocity. What percentage of fuel is consumed? Meaning, if it started with 100 liters, what is the amount of fuel left at the point 1? What is the amount of fuel left at the point 2? What is the amount of fuel left at point 3? And stuff like that. So they have estimated these things. So landing and takeoff, it's easily estimated because most of the aircraft around have the same kind of fuel consumption in that part. And in this climb too, very similar climb and descent will be similar. Large part of the fuel consumption in passenger aircraft will be from in the cruise condition, where it is going to fly at that altitude, at that Mach number for a long time, 5 hours, 6 hours, like that. So these things will be small. So if I can plug in this W1 to W0 and this 6 to 7 and all that from existing data, then I get a very good estimation of the fuel consumption. Okay, so now let's look at what is there existing in available information. Some segments like takeoff, climb, descent, approach, and landing consume negligible amounts of fuel. But that is negligible only as compared to the total mass. Of course, they do guzzle a lot of fuel, but compared to what they'll be doing in cruise, there's going to be very, very small fraction. Okay, and maximum fuel consumption is in loiter or in cruise condition. That's a major component of any civil aircraft. Dogfight, pursue, dash in case of combat aircraft. If it is civil, then it's cruise and loiter. And dogfight, pursue, and dash in terms of combat. So dash is when the aircraft goes supersonic. And when the aircraft goes supersonic, as we have all mentioned earlier, the CD0 goes more than a factor of 2, double. So the fuel consumption simply shoots up. So most combat airplanes do not use supersonic flight as a normal. They only use it as part of a dash, in the sense to evade a missile or to come back from enemy territory. So formulae derived from the previous models are to be used for range and endurance. So range and endurance, we already talked about how to estimate the fuel, the initial and the final fuel consumption in range and endurance. But for the other things, the takeoff and taxi, the ratio will be 98%, meaning that if you started with 100 liters from taxi to takeoff, you would have consumed 2 liters. Okay, from takeoff to climb, it is 0.97. So 3% of whatever is left. So if I'm looking at total fuel consumption, sorry, taxi, takeoff to climb, then I have to multiply these two, 98 into 97. That will be the amount of fuel left after climbing to the cruise condition. Then descent and approach and landing are on similar numbers. A slightly less fuel consumption when you're descending rather than climbing, as you can notice, not very significant, but it's still there. Because while descending, your thrust is reduced significantly. While takeoff and landing, your thrust is at takeoff, it is at maximum. So approach and landing, you are at a minimal thrust, mostly dictated by safety considerations. You don't really switch off the engine into idle condition and stuff like that. So fuel consumption statistic for different stages of flight, and again, a little more detail for what kind of aircraft you're looking at, and home build, single engine, twin engine, the same numbers are there. And supersonic flight things, cruise airplanes, all of them are around the same thing. So 9.98 to 9697 around that. So they don't change much. So this can be used. Now we are left with only two components in this picture. One is the range. Okay, and if it is not the range, but the endurance, which is a design driver, for that amount you have, because you have already estimated the fuel from 0 to 1, 1 to 2, similarly from 3 to 4, 4 to 5, 5 to 6, and 0 to 1, 6 to 7. So now the major part of the fuel consumption, which happens in cruise, is what you're supposed to estimate. Okay, how do we estimate that? For that, you need multiple things. You need to estimate what is the lift drag ratio, and you need to have what is the specific fuel consumption. Okay, so drag ratio is difficult to estimate at this point because you have no other parameter. So what you can do is you can take the specific fuel consumption and the type of jet engine you have chosen, and you can say that, okay, this engine is going to fly for 6 hours. And this roughly this number, this many kilonewtons of thrust I need. 6 hours, you get a fuel consumption estimate. And that may not be the most ideal in the sense because you're not used the actual range equation in terms of L by D and all that. But to get a fuel consumption estimate, you will be able to, you're good enough in using that kind of thing. So typical parameters, as I said, breakaway equation has these parameters in terms of L by D and other issues for fuel consumption. So again, there is a collection of data. I think this is from Roskamp's book, and I just highlighted fighter plane. Their L by D is changing from 4 to 7, and remember most of the L by Ds is roughly 10 plus the aspect ratio in a big aircraft, but less than that for fighter planes. So transport jets, you get 13 to 15 because their aspect ratio is close to 6 or 7. So you get around 13 to 15 L by D, and then fuel consumption and all that. So for loiter, what is the L by D? So you can from this get an estimation of the fuel consumption, because for using breakaway equation, you need L by D, you need SFC, and you need range, distance and range. So you can work backwards and find out what is the fuel mass ratio from the initial to final. So there's another estimation fuel technique which is there, and anyway, all of them depend on the same bunch of equations we have used. CD is equal to CD naught plus KCL square, and then logarithm of F. These are curve fit curve fits of data. Now, if you see here S wet, which is the wetted area, so this will give you an estimation of the skin friction drag. And you need an estimation of the skin friction drag because you want to get the CD naught correctly, this part. Okay, and K you have to assume because you have not decided on the aspect ratio and the epsilon factor. So assumption of K, you will get you a reasonably good estimation of D and CD, and that from that drag and the kind of thrust you need. So specific fuel consumption, there are two types of specific fuel consumption. One is for propeller engines, which is usually told as newtons per kilowatt hour or pound per HP hour. Okay, and if you have 1 pound per HP hour, then you just convert it into 6 newtons per kilowatt hour. For jet engines, it's usually the old units, the pounds per pound hour, or in our case, it's kilonewtons per kilo hour. One thing you remember, while these numbers are given in terms per hour, in your equations for endurance and range, it has to be in seconds. So you have to ensure these factors are in the seconds unit. Okay, so otherwise you'll get a ridiculous number. So typical values are shown here for high bypass turbofans. You have something like 0.4 pounds per pound hour, and for loiter you have a little more, and then all units are British units. For turboprops you have 0.5 to 0.8. High bypass ratios, as you see, they're almost as good as piston engine aircraft. So that's the reason you're going for high bypass. Unfortunately for fighter planes, you need to have a low bypass, and there the fuel consumption you can see is significantly higher than what you would expect in a turboprop or a piston engine. So some data from Jane's All the World 1995-98 selection. This is different engines, CFM, IAE, and Pratt & Whitney, and R&B, Rolls-Royce Trent, and Zuld, some Russian engine. So which powers antenna, antenna 12, antenna things like that. Boeing 777 and MD, one Airbus 380, they all use Pratt & Whitney 4XXX series. Pratt & Whitney JT9D is used in Airbus 310. So these are the actual engines. Now these are not some old fashioned engines. So all the Airbuses and all, you have the CFM. This is a consortium engine. So their fuel consumption is also given in terms of pounds per pound hour or milligrams per Newton second, things like that. So you choose aircraft engine and you can get a decent estimation of the kind of fuel consumption you're looking at. Okay, and some past data we also need for propeller, right? You don't know what aircraft you're going to design. So for propeller aircraft too, you will have some data from existing things. For a jet aircraft, what will be the areas? This is for wing areas, and because you need to have a wing loading. So you see here, WTO, this in pound, this is in feet square. Power is in HP. So this will only give you an idea of what will be the kind of wing loading for propeller aircraft, wing loading for jet aircraft, and things like that. Okay, so essentially, this is the kind of thing which from which you start looking at the total weight of the aircraft. So you made an estimation of the aircraft weight. Using both statistical data of the existing successfully built aircraft, as well as some detailed estimation using fuel consumption and the type of engine, right? So next is what is called the constraint analysis. Okay, before going into that, I'd like to stop here and stop the recording so that we can have a question answer session. Hold on.